A reactor milestone is not a power system. That sounds like a technical distinction, but in advanced nuclear energy, it is the distinction that decides almost everything. In China, a real experimental milestone has taken place around a thorium molten-salt reactor program. The source-locked record supports a built 2 megawatts thermal liquid fuel, thorium molten-salt, experimental reactor, and an institutional report that, in 2025, the program achieved in-reactor thorium-to-uranium conversion verification. SIN, AP, and CAS describe direct evidence concerning key nuclide evolution characteristics. Those are not trivial claims. They matter because they move part of a difficult reactor and fuel cycle architecture out of the realm of pure promise and into contemporary experimental evidence. But that is not the same as saying China has a deployable thorium power plant. It is not the same as saying the system is generating commercial electricity. It is not the same as saying it is connected to a grid, serving a hospital, running without maintenance, ready for export, or available at commercial scale. The real story is more interesting than the exaggerated one. A genuine reactor milestone is significant enough without turning it into fiction. So this episode is not about asking whether the Chinese TMSRLF1 milestone is real. On the controlling evidence, the experimental milestone is real. The better question is what kind of milestone it is, and what it still does not prove. The answer gives us a better way to evaluate advanced nuclear claims generally. Reactor physics can move forward before the rest of the power system is ready. Fuel cycle evidence can improve before there is a commercial fuel cycle. Thermal operation can be source-locked before electrical output is established. A research reactor can be important without being a deployable energy product. That is the central distinction. Having a reactor is not the same as having a repeatable power system. To see why, start with what TMSRLF1 acts. Having a reactor is not the same as having a repeatable power system. To see why, start with what TMSRLF1 actually is. The source record identifies TMSRLF1 as a 2 megawatts thermal liquid fuel thorium molten salt experimental reactor. The word experimental matters. The unit matters too. Megawatts thermal is thermal power. It refers to heat. It is not an electrical output claim. Electricity requires a power conversion system and evidence that useful power is delivered outside the reactor boundary. In the acquired controlling sources, that electrical output evidence is not established. This is not a semantic quibble. If a reactor produces heat, that is a real engineering event. But a power plant has to convert heat into useful energy service. It has to move heat through equipment, manage controls and safety systems, integrate with a load or grid, operate under regulatory conditions, and do all of that repeatedly enough to become infrastructure. An experimental reactor can be the beginning of that chain. It is not the chain. The fuel cycle claim has the same structure. SIN, AP, and CAS institutional sources report thorium-to-uranium conversion verification in the built 2 megawatts thermal liquid fuel, thorium molten salt, experimental reactor. A related SIN-AP source reports completion of an in-reactor thorium-uranium conversion principle verification experiment and acquisition of direct evidence about key nuclide evolution characteristics. For a thorium molten salt program, that is meaningful because thorium is not simply a magic fuel that becomes commercial power by being named. It has to participate in a managed fuel cycle. It has to be converted, measured, controlled, and eventually integrated into a system that can operate reliably. But fuel cycle verification is not the same thing as a closed commercial thorium fuel cycle. The controlling packet does not source lock raw isotopic data. It does not source lock a complete commercial fuel processing pathway. It does not source lock fuel logistics for a deployed fleet. It supports the narrower statement. The operating institution reports an in-reactor thorium-to-uranium conversion verification milestone and direct nuclide evolution evidence as a program claim. That is important. It is still a layer, not the whole system. This is where many technology narratives fail. They collapse layers. A reactor works so people infer a power plant exists. A fuel cycle experiment succeeds so people infer a commercial fuel cycle is solved. A thermal rating appears so people infer electrical output. An official milestone is announced so people infer full deployment. In advanced nuclear energy, those inferences are exactly where the risk enters. The deployment stack is larger than the reactor. At the first layer is reactor physics. Can the nuclear process be initiated, sustained, controlled, and studied under the relevant conditions? At the second layer is fuel cycle evidence. Can the fuel behavior, conversion pathway, or nuclide evolution be observed and bounded? At the third layer is engineering qualification. Can the materials, salts, pumps, heat exchangers, seals, valves, instruments, and control systems survive the actual chemical, thermal, and radiation environment? At the fourth layer is system integration. Can the reactor, fuel handling, heat transport, safety systems, balance of plant, and external load operate together as one system? Then comes regulatory validation. Can the safety case be reviewed and approved, not merely described? Then manufacturing. Can the design be built again with qualified components, reliable suppliers, controlled tolerances, and predictable quality? Then operations. Can trained teams inspect, maintain, repair, refuel, or process fuel as required, handle outages, and keep the system within its safety case over time? Then economics. Can the delivered energy justify the capital cost, operating cost, fuel cycle cost, outage risk, maintenance burden, financing, and industrial organization required to repeat it? Only after that does the word deployment become serious. That sequence is not a bureaucratic obstacle course. It is the structure of the technology. Evidence at one layer does not automatically validate the next layer. A reactor physics result does not qualify component lifetime. A fuel conversion observation does not prove a commercial fuel cycle. A thermal reactor rating does not prove electrical service. A regulatory inspection outline title does not substitute for full public license closure. A pilot milestone does not prove manufacturing repeatability. A national program claim does not prove delivered power. This is why TMS-RLF1 should be treated neither as a miracle nor as an irrelevance. The miracle framing is wrong because it turns one layer into the whole stack. The dismissal framing is wrong because it ignores that one layer really has moved. The evidence-led position is more disciplined. China has advanced an important experimental molten-salt reactor and thorium conversion layer. The source-locked record does not show deployable energy infrastructure. Now look at the molten salt part of the story. Molten salt reactors are strategically interesting because they can change the constraint map. The source-locked material supports program claims around high temperature output, normal pressure characteristics, and reduced dependence on conventional water cooling assumptions. Earlier SINAP materials associate TMS RLF1 with Wu-Wei, Gansu, an arid location, and later institutional sources describe no water cooling and normal pressure characteristics as advantages of molten salt reactors. Those features matter. High temperature can be valuable for efficient heat use or industrial applications. Normal pressure characteristics change some safety and engineering questions compared with high-pressure water systems. Reduced cooling water dependence could matter in places where water availability constrains power infrastructure. But changing constraints is not the same as eliminating constraints. Molten salt does not make engineering disappear. It moves engineering into different places. Fuel salts create demanding chemistry. Structural materials have to survive corrosive environments, high temperature, radiation, and fission product effects. Component lifetime becomes a core question. Heat exchangers, pumps, seals, valves, and instrumentation have to operate in conditions that are not forgiving. Salt chemistry has to be managed. Fuel processing and recovery have to be designed, qualified, and integrated. The source-locked packet gives concrete examples without requiring us to invent failures. SIN-AP program material discusses interactions between fuel media and structural materials, corrosion suppression, precision fabrication, pumps, heat exchangers, valves, seals, high-temperature fluoride salt equipment, alloys, loop operation, and maintenance experience. SIN-AP materials evidence identifies tellurium embrittlement as a service life and safety issue for in-reactor metal components. SIN-AP fuel recovery evidence discusses thorium tetrafluoride and flyby systems and points to issues such as energy consumption, low efficiency, poor decontamination, and aggravated corrosion in that domain. Those examples should not be exaggerated into a claim that TMSR-LF1 has failed. That is not what the evidence says. Their role in the story is different. They show how the bottleneck can migrate. At the concept stage, the question is whether the reactor idea can work. At the experimental stage, the question is whether it can be demonstrated and studied. At the engineering stage, the question becomes whether chemistry, materials, components, inspection, and maintenance can survive long enough to support useful service. At the deployment stage, the question becomes whether the whole system can be licensed, manufactured, operated, financed, and repeated. That migration is normal. It is also why the headline version of advanced nuclear is so often misleading. The reactor is the most visible object, but it is not the whole burden. A deployable power system includes the reactor core and fuel chemistry, but also heat transport, power conversion, safety systems, controls, sensors, emergency systems, operating procedures, regulatory records, supply chains, spare parts, trained operators, maintenance intervals, fuel logistics, waste or used fuel handling, and an economic reason for someone to build the next one. If any of those layers is missing, the system may still be a serious research milestone. It is not yet a repeatable energy infrastructure product. This is the analytical center of the episode. Reactor physics opens the door, but the deployment stack decides whether the door leads anywhere. The China framing has to be equally careful. It would be a mistake to dismiss the milestone simply because it is not a commercial power plant. Contemporary experimental evidence in a difficult thorium molten-salt architecture is meaningful. It can produce institutional learning. It can strengthen materials and fuel cycle expertise. It can give regulators, engineers, and program managers experience that paper studies cannot provide. It can support the next layer of demonstration work. It would also be a mistake to convert that achievement into comprehensive deployment leadership. The controlling record does not show commercial electrical output from TMSR-LF1. It does not show grid service. It does not show a closed commercial thorium fuel cycle. It does not show mass commercial availability. It does not show the detailed operating record needed to answer sustained service questions. So the strategic significance is not China has solved thorium power. The strategic significance is China has moved an important experimental layer forward in a technology family where experimental layers matter. That distinction also changes how we should compare countries. The question is not simply who has a reactor. It is who can move from reactor evidence to validated systems. Who can qualify materials under molten salt chemistry, temperature, radiation, and lifetime conditions? Who can build reliable pumps, heat exchangers, vessels, seals, instrumentation, and control systems? Who can validate fuel processing without pretending a conversion result is the same as a commercial cycle? Who can make regulatory evidence legible enough for deployment? Who can manufacture specialized components at repeatable quality? Who can operate, inspect, maintain, repair, and finance the system over years rather than headlines? Who can deliver power to real loads with reliability that customers and grids can use? That is the scoreboard. It is less viral than a claim about a reactor that runs a hospital for decades. It is also much closer to how infrastructure actually emerges. The misinformation angle is useful only if it stays in its place. Separate real technologies can be rhetorically combined into a deployed system that does not exist. Real molten salt research, real thorium fuel cycle work, real historical molten salt experiments, and real electrochemical ideas from other domains can be blended into a story about a ready-made generator. But the existence of real fragments does not prove an integrated architecture. That is why we should not open the story by pretending the 50-year saltwater hospital claim is an unresolved mystery. It is not the strongest frame. The stronger frame is that the real milestone is already significant, and significance does not require fiction. A viewer should come away with a cleaner mental model. Reactor physics asks whether the nuclear system can work. Fuel cycle evidence asks whether the fuel behavior can be verified and managed. Engineering qualification asks whether the equipment can survive. System integration asks whether the parts work together. Regulatory validation asks whether the safety case can be approved. Manufacturing asks whether the system can be built again. Operations asks whether it can be maintained in service. Economics asks whether the delivered energy can be repeated at a cost and reliability someone can actually use. Every layer needs evidence. Every layer can become the bottleneck. And progress at one layer should be recognized without being promoted into proof of the next. This also explains the limited connection to rising firm power demand. Data centers, industrial electrification, and other large loads increase interest in dense, reliable, low-carbon firm power. That makes advanced nuclear more strategically relevant if it can be deployed. But it does not mean TMSRLF1 is serving artificial intelligence infrastructure today. It does not mean an experimental reactor has become a data center power product. It means the value of repeatable firm power is rising, which makes the deployment stack more important, not less. The ending has to return to the central measurement. A scientific milestone can be real. A reactor milestone can be important. A fuel cycle verification can change the evidence status of a program. But infrastructure asks a different question. Can the system repeatedly deliver useful power under real operating, regulatory, manufacturing, maintenance, and economic constraints? That is the difference between a reactor and a power system. For TMS-RLF1, the evidence-led conclusion is narrow and strong. China's milestone is real. The viral deployment interpretation is premature. Molten salt changes the constraint map, but it does not remove the need for materials, qualification, fuel cycle work, component lifetime, system integration, regulation, manufacturing, operations, and economics. Strategic competition will not be decided by the existence of one experimental reactor alone. It will be decided by who can turn validated layers into repeatably deliverable power. The reactor matters. It is just not the power system. For the full story behind China's thorium reactor and what it actually means for the future of energy, watch the full episode of Quantum Convergence: Energy.